Eigenface method opens a door for us to know that when we do face recognition, we don't necessarily directly describe the visual appearance on the face, but rather we would like to describe the variation mathematically so that we can approach a systematic face recognition method. And in the following material, we would like to introduce another very important and typical face recognition method called Fisherfaces. And this work was published in 1997. And this paper was published to improve Eigenface. The goal of Fisherfaces is they try to develop an approach insensitive to large variation in lighting and facial expression. And this were the problem that would damage the Eigenface approach. So we just remember that in the Eigenface approach, they just worked on the frontal face with the perfect lighting condition, and without different facial expression. But if we work on the face images with facial expression or lighting variation, the Eigenface approach may fail. So in this paper, they have some observation and they try to develop a new mathematical model to do a more accurate face recognition. The first observation is that all images would lie in a 3D linear subspace of a high-dimensional image space. That means we think that the distribution of the face image may not be so simple, may not be simple as a linear combination of some basic basis. And this was the assumption of the Eigenface, because we also remember that the Eigenface is actually the eigenvector of the covariance matrix, and we use linear combination to describe a face image based on the linear combination of eigenfaces. But here they say that the real space may not be described by linear combination. Okay. The second observation is that certain regions of the face may have variability from image to image that often deviates significantly from the linear subspace. So again, they propose that the variation cannot be well described in the linear subspace. And this sample image show the challenge case the Fisherfaces approach want to handle. So from the subset 1, we see that the light is basically frontal, okay? And from subset 1 to subset 5, we can see that the lighting moving from the front of the face to the left of the face, so that we can see here at subset 5, the light source is at the left part of the human, so the right face of this human is dark. Okay, and this is the first row, and from the second row, the lighting angle may be from the above, from the top of the head. Okay, so here we can see that this is a light from the top of the head, and on the contrary, at the third row, the lighting source is from the bottom of the face. So here we can see here. Okay, so in such variation is in such face image database with large lighting variation, the Eigenface approach will fail. So in this paper, they try to use a derivative of Fisher's linear discriminant method that maximizes the ratio of between class scatter to that of within class scatter. So theoretically, when we want to do good classification, we want to put data belonging to different classes as far as possible, and then put data belonging to the same class as close as possible. Okay, so the formulation of this paper is that they try to maximize the ratio of the between class scatter to that of within class scatter. And in eigenface, PCA, principal component analysis, yields projection direction that maximize the total scatter across all classes. Therefore, it's not so appropriate to discriminate different classes of data. So the variation between the images of the same face due to illumination and the viewing direction are almost always larger than the image variation due to change in face identity. Therefore, if we handle such, if we are working on such challenging database, the eigenface approach may put more effort on modeling luminous and viewing direction change rather than the face identity change. Okay, because the eigenface approach just simply use a linear combination, and the goal of the PCA is to make the variation as large as possible when they do the projection. So before we go into the Fisher's linear discriminant, we revisit at the eigenface approach. So let's consider a set of n sample images S1 to Sn, and taking values in n-dimensional image space. Okay, and assume that each image belongs to one of the C classes S1 to XC. So let's also consider linear transformation, mapping the original n-dimensional images into m-dimensional feature space. So this m-dimensional feature space is actually composed of m eigenvectors, and then the feature vectors yk yk is equal to w transpose sk. That means sk is the original images, and the wt is actually the eigenvectors. And when we do this inner product, we get the component corresponding to the case eigenvector. Okay, so we use such coefficient to describe a face image. Okay, so we can see here the w is m by m, and it is a matrix with orthonormal columns, and we can use it as a projection matrix. We project an n-dimensional images into m-dimensional vector. With such definition, the total scatter matrix ST is defined like this. So here we show the scatter matrix in the original space. So we can see here sk minus mu multiplied by sk minus mu transpose, where mu is an n-dimensional vector and is the mean averages of all samples. So here we describe how the total variation of the all face images to the mean face. Okay, and after applying the linear transformation W transpose, the scatter of the transform feature vectors is actually W transpose STW. And here are some derivation. So in the projected space, the scatter matrix is summation k equal to 1 to n, and then yk minus the projection value, yk minus the projection the projection value of the mean face. And then we can rewrite yk as W transpose sk, and then we can multiply them and then take the W transpose out, and then we can see this value And then now we can do this simple algebraic process. So U transpose W, and then we also take the W out, and then we can get this, and this is the matrix ST. Therefore, we know that the scatter matrix in the projection space is W transpose ST W. Okay, and in PCA, the projection WOPT is chosen by maximizing the determinant of the total scatter matrix of the projected samples. Therefore, how do we find the best projection matrix W? That is, we try all possible matrix W such that the scatter matrix is maxima. Okay, and the solution of this optimization problem is that we just selected the m eigenvector, the m eigenvectors of ST corresponding to the m largest eigenvalues. Okay, and this is the core procedure of the eigenphase approach. And if you still remember linear algebra, this is actually the orthogonal diagonalize the matrix ST, because the W is the orthonormal matrix. Okay, but in Fisherface, we try to maximize the ratio of within class scatter, the between class scatter to within class scatter. So we try to use class-specific linear method for dimensionality reduction rather than PCA. Here we use Fisher's linear discriminant, or sometimes we call it LDA in short. This method selects W in such a way that the ratio of the between class scatter and the within class scatter is maximized. Therefore, the objective function of the optimization problem is different. So the between class scatter would be this SB. SB is equal to summation I equal to 1 to C, and then UI minus U, where UI is the mean vector of the I's cluster, okay, and the mu is the mean vector of all samples. Okay, and this is the between class scatter, and the within class scatter is that SW is equal to summation I is equal to 1 to C, and then summation SK belonging to XI, where XI is a class. Okay, so here we just calculate this formulation is just calculate the within class scatter matrix of the I's class, and then we sum all class. Okay, so this is the within class scatter. The between class scatter means you can see that, you can imagine that the between class scatter is the total difference between the phase images belonging to different classes, and the within class scatter means the total difference of the phase images, okay, belonging to the same class. Okay, and we try to maximize this value. Okay, we try to maximize this value. So if SW means that is within class scatter, if SW is non-singular, that means it is invertible, then the optimal projection is chosen as the matrix with orthonormal colors, which maximize the ratio of the determinant of the between class scatter matrix of the projected sample to the determinant of the within class scatter matrix of the projected sample. Okay, so here we see that this is actually the within class scatter value of the projected samples, and we take determinant. Okay, and this is for between class scatter. And then remember that in linear algebra, when this matrix is invertible, we can feel safe to calculate this value, okay? Because when it is invertible, then the determinant will not be equal to 0, then the denominator will not be equal to 0, okay? So after many mathematical derivation, how can we determine the best W? The solution is the Wi is the set of generalized eigenvectors of Sb and Sw corresponding to the m largest generalized eigenvalues. So after many derivation, we can reduce this problem to this one. Sbwi is equal to lambda I Swi, and this is a generalized eigenvalue problem. They connect the simple eigenvalue problem is Ax equal to lambda x, and right here Sb something like A, and x something like this value. Okay, so it's not a baseline eigenvalue problem, but it is a generalized eigenvalue problem. And theoretically, at most C-1 non-zero generalized eigenvalue problem would be calculated. Okay, so when we try to find an m-dimensional space to do the projection, the m value is less or equal to C-1. And then geometrically, what is the difference between PCA and LFT? PCA actually smears the classes together so that they are no longer linearly separable in the projective space. So assume we have two classes of data. One is circle, another one is cross. And when we use PCA to find the projection, we would find the axis that maximize the variation of data. Therefore, we will find this axis, and then we project the data onto this axis. So this one project to this one project to this one, and so on. So we make the variation of the projected sample as large as possible. However, when we use FLD achieves greater between classificator, and consequently classification is simple. So if we use FLD, we will find this axis. And you will see that the variation of the projected sample is not as large as the PCA. However, all cross sample will be projected at this side, and all circle sample will be projected at this side. So it will be much better for us to do classification so that we can discriminate different classes of phase images. Okay, but unfortunately, the within class scatter matrix SW is always singular. That means the denominator of the formulation may be equal to 0. That would be a mathematical problem. Okay, the rank of SW is at most n-c, and in general, the numbers of images in the learning set n is much smaller than the numbers of pixels in each image. So this is why this matrix is always singular. And it's possible to choose the matrix W such that the within class scatter of the projected sample can be met exactly 0. Okay. So the solution is we actually use PCA to reduce the dimension of the feature space to n-c, and then apply the standard FLD to reduce the dimension to C-1. So that's a compromise to make this mathematical model work. So the final formulation is that the best projection matrix is given by the multiplication of FLD matrix and the PCA matrix. Because first we find the PCA matrix, by PCA, we find the best projection. We do linear projection first to reduce the dimension from n to n minus c. So the optimization for WPCA is performed over an n by n minus c matrix. And then after we do such linear projection, we find the best projection matrix that maximizes the ratio. Okay, so the WFLD is performed over n minus c times by m matrix to find the orthonormal column. So this is the final formulation. So in computing WPCA, we have thrown away only the smallest C-1 principal components. Now let's go to the experiment. They designed a dataset called Harvard dataset. Now let's go to the experiment. They designed a dataset called Harvard dataset, and lighting has been systematically varied. There are 5 subsets. The subset 1 consists of 30 images with light source direction within 15 degrees of the camera axis. Subset 2 consists of 45 images with light source direction within 30 degrees. And then subset 3 consists of 30 images with light source direction within 45 degrees. The fourth subset consists of 30 images with light source direction within 60 degrees. And the final subset consists of 30 images with light source direction within 75 degrees. And then classification was performed using a nearest neighbor, just nearest neighbor classifier. This is the sample images to show the direction of the light source. And they designed several experiments. The first one is the extrapolation experiment. That means they would like to train based on subset 1 and then test based on subsets 1, 2, and 3. So this is called extrapolation because we use the most simple method to do training, but we test with harder face images. The second experiment is interpolation experiment. So we will train based on subsets 1 and 5. So the most simple one and the most difficult one. And then test based on subset 2, 3, and 4. And this figure shows the result. The x-axis means the data, different data, okay, and the y-axis means the error rate, and this is the result of the extrapolation experiment. And here we can see that by training based on the subset 1 and the test based on subset 1, all method was good. But for the second subset, we see that the eigenface, the error rate of the eigenface increase, and the feature face does not increase significantly. And for the third subset, the error rate of the eigenface increased to 40%. Okay, and there's some method proposed after the original eigenface approach is that they suggest to throw away the first 3 eigenvectors. If so, we can reduce the error rate. However, this error rate is still significantly larger than the error rate achieved by the feature face. Therefore, from this result, we can see that the eigenface approach does not work very well when there is lighting variation. Okay, So we can see several conclusions. All algorithms perform perfectly when lighting is near frontal, but in the eigenface method, removing the first three principal components result in better performance. And the Fisher method has had error rate lower than the eigenface approach. And this is the interpolation experiment, result of the interpolation experiment. We can see that the error rate of the eigenface approach are quite high. Okay, and the correlation approach is another approach, is another method proposed before the Fisherface. And from here we can see that the Fisherface has very accurate result. Okay, for three subsets. They also work on different data set. So for 16 subjects, okay, 10 images were acquired, and the last 5 images were acquired with different expression like happy, sad, winking, sleepy, and surprise. And there are 2 different scales, full space or closely cropped. So this is full space, and the close cropped face may be from the top of the eyes and to the bottom of the mouth. They tried these two different cases, and this is actually the Yale database that has been widely used in many face recognition studies. And the Yale dataset was designed to evaluate the performance when there are different facial expression or there are lighting variation, and sometimes when there are some occlusion object. To compare the performance of eigenface and the Fisherface, they first determine the numbers of principal components using the lowest error rate in the eigenface method. So we compare with the best eigenface result. Okay. And finally, they found that the 30 principal components are retained in the following experiment. In this result, in this figure, we show the numbers of principal components versus the error rate, and we can see that when the numbers of components is reduced to around 30, if the numbers of components is 30, then we may achieve almost the best error rate, that is 45% or 50%. However, when we use the Fisherface approach, the error rate is just 7.3%. And because the Fisherface, we have a theoretical dimension. Okay, so we don't need to do, because we theoretically we only have C-1 Fisherface. Therefore, we don't have to determine the base projection, the best dimension of the projection space. Okay, so again, we see from this data set, the Fisherface approach works much better than the Eigenface approach. The Fisherface method had error rate that were better than half of that any other method. So we compare eigenface, correlation, linear subspace. This is not clear. Okay, and this is Fisherface, and then we work on closed lookup and the full face approach. And we see that there is a trend when we consider the full face, we may get better performance. Like here, if we consider the full face, we have much smaller error rate than just consider the closely cropped face. So the Fisherface method tends to discount those projections of images that are not significant for recognizing an individual. the mouse, for example, the mouse, since it varies quite a bit for different facial expression. Here are the numerical result. We can see that for the closely cropped face, the error rate of Fisherface is 7.3. But if we consider the full face, the error rate is just 0.6%. So all the algorithms perform better on the images on the full face, and a dramatic improvement in the Fisherface method that was much better than the Eigenface and its variant. When the method is trained on the entire face, the pixel corresponding to the occluding tool of the face are chosen as good features for discriminating between individuals. So not only the appearance of your eyes, nose, and the mouth, the contour of your face is also very important due to face recognition. And the overall shape of the face is a powerful feature in face identification.